All right, so this is topic 18, which is just the HL version of topic 8, acids and bases. So today we're just kind of talking about another definition, which is the Lewis acids and bases. So it's going to be different from Bronsted-Lowry. And so one of the videos that you guys have on Canvas that was pre-made, it's actually the second one. It actually compares, it has like a good table, like a summary thing in it, where it compares and contrasts like Bronsted-Lowry versus Lewis and sort of their definitions and kind of which types of things could be, because there are some chemical or some molecules that can be both, like a Bronsted-Lowry acid and a Lewis acid, but then there are some that they can only be Lewis acids. They can't be Bronsted-Lowry acid. And then the same thing for the bases. So it kind of goes through, but we're doing this 18.1. So our basic definitions, and we'll talk about them when we get to this section, but we're not talking about protons. Now we're talking about lone pairs or electron pairs. So that's the basic definition for Bronsted-Lowry. It was, you know, acids donate protons and bases accept protons. Well, with Lewis, you're accepting and donating electron pairs, lone pairs. And so they're opposite, because acids, they donate protons, but they accept lone pairs of electrons. And bases for Bronsted-Lowry, they accepted protons, but for Lewis, they donate the electron pairs. So they're kind of opposites, and that always like trips people up. And then this is going to kind of relate back all the way back to like the topic, the HL topic 3 stuff, which was topic 13, where we talked about the coordinate covalent bonds, and then even the complex ions and the ligands. Because when you have a Lewis base and a Lewis acid react, it's forming one of those coordinate covalent bonds because something is donating a pair of electrons instead of each item or each thing donating one electron to make the bond. They're both coming from one substance or one atom. Okay. And then we're going to start talking about some new vocab, because this is going to relate to organic chemistry, which we haven't gotten to yet. But there are these terms in organic chemistry, nucleophile and electrophile. And that's what we use to describe a Lewis acid or base if it's an organic molecule. So I'm going to go ahead and skip down here so we can get started. Okay, so I already kind of mentioned the basic definition. So Lewis acid is a lone pair acceptor or electron pair acceptor. You don't necessarily have to say lone pair. If you just say electron pair acceptor, that's fine. And then Lewis base is a electron pair donor. Okay. And so anytime you have a Lewis acid and base reacting, they're going to form a coordinate covalent bond. And so this is kind of showing us an example. The biggest example of a Lewis base is ammonia, NH3. It's really common. It's used a lot. And so it has this lone pair of electrons right here on the nitrogen that it can donate. And so that makes it a good Lewis base. Boron trifluoride, BF3, is a really common non-organic example of a Lewis acid, because boron has that incomplete octet. Okay, remember that everybody likes to have 8, they like to have a complete octet, but boron was one of the exceptions we talked about, that usually it only has 6 just because of the number of bonds that it makes from where it starts on the periodic table. But it can make another bond because it doesn't have a lone pair or a fourth bond over here. And so what happens is the nitrogen here donates its electron pair, and the boron trifluoride, the boron accepts them, and it forms this coordinate covalent bond right here between the nitrogen and the boron. Okay, and so it makes this kind of big giant molecule. Okay. Sorry, they're coming on announcements right now. Other common things that we've seen sort of in the past, transition metal ions in solution are Lewis acids. So this relates back to the whole complex ion ligand thing that I was mentioning. So when you have complex ions with ligands, the transition metal is considered a Lewis acid, and the ligands are always Lewis bases. And so the most common one that we had for the ligand was always water. There were other things that we talked about. And if you look at that video that I mentioned where they're comparing them, the table, it summarizes, it gives you a few more examples other than water. But just know that when you're talking about a complex ion, you're talking about a coordinate covalent bond forming, because each of these water molecules, the oxygen has a lone pair, actually has 2 lone pairs, but it's going to use one of its 2 lone pairs to make a coordinate covalent bond to that metal ion. Okay. And so this is again kind of tying in like topic 3 and 4 with topic 8, bonding and complex ions and all that kind of stuff. And so we're seeing how this definition kind of relates back to those types of bonds and how they were formed. So that's all sort of inorganic with the transition metals and the complex ions and things like that. In terms of organic chemistry, we're going to see Lewis acids and bases kind of called slightly different terms. And so nucleophiles, we call them, those are electron-rich species. So if you're electron-rich, that means you got lots of electrons to give away, okay? And so nucleophiles are electron-rich species that donate a pair of electrons. Therefore, nucleophiles is kind of like almost like a synonym for Lewis bases when we're talking about organic compounds or organic molecules. Electrophiles, they are electron deficient. Okay, that means that they don't have any. They want to accept a lone pair of electrons or a yeah, sorry, I don't know what I'm trying to say. I lost my train of thought. And so electrophiles is kind of another term for Lewis acids when we're talking about organic compounds. And so the most common examples for nucleophiles, you have the hydroxide ion, you have the chloride ion, and then ammonia, which we saw up there earlier. Boron trifluoride is a good Lewis acid. And then these things are called carbo cations, because it's got a positive charge, so it's a cation, and it's got all of these carbon groups on it, okay? And then the copper ion in those with those transition metal complexes. So again, when you look at the video that's recorded on Canvas, that table summary, it gives you, and it even separates them. It says like these are good like non-organic examples and these are good organic examples. And so definitely go look at if for no other reason, so that you can kind of add that table in here somewhere, and so you have that good summary to refer to. And so basically today you just have a few questions. You're kind of talking about the definitions we talked about, how can things act as a Lewis acid and base, and kind of describing sort of how those coordinate covalent bonds would form based on that electron pair being donated and accepted. Okay.
Okay. Curtis said that he tried